Very well, we can start. So it's a pleasure to have again Eric Lescano with his second lecture on alpha prime corrections and their double formulation. Please, Eric.
Thank you very much. Well, I'm going to start reviewing some topics of the previous lecture. In the previous one, we have studied the low energy limit of closed string field theories. We focus on fields and massless fields. We focus on symmetries and we find the action. We described bosonic string, type 2 superstring, and the heterotic superstring. We focus on this Lagrangian or this action. The action for us is this one. Recall that this D is the dimension of the target space. We are focused on this Lagrangian. We have a metric tensor over here. We have a scalar, dilaton, and we have a two-form. This is our Lagrangian. And we are integrating out massive fields. So this Lagrangian contains alpha prime corrections. And these alpha prime corrections are 4 derivative terms for us. Of course, we have a tower of alpha prime corrections. For example, in the bosonic string, we have Riemann square term. But if we analyze higher orders, you will find Riemann cubic terms, Riemann to the 4 terms in the bosonic case. Type 2 superstring has his first non-trivial corrections at the cubic level. So we are not going to study type 2 in these lectures. And finally, in the heterotic case, we have alpha prime corrections. We have Riemann square term, but also we have Chern-Simons terms, H times Chern-Simons terms in this heterotic formulation. So we are always analyzing the low energy limit. The symmetries of this Lagrangian was diffeomorphisms and abelian gauge transformations. In the case of the heterotic string, we add here an extra term just for the heterotic case. We have here an extra term. Let me change my color. We include here this term. It's a Young-Mills term. And today you are going to see why we are including this field over here. This is an extra massless field in the heterotic case. And we are always focused on the gravitational terms. So perhaps this extra term over here may be strange because we are not focused on Young-Mills corrections, for example. We want to correct just the blue part, but this extra term will be important for us today, as you are going to see. So about the alpha prime corrections, we have different ways to compute these higher derivative corrections. In the previous lecture, we talked about scattering amplitudes. We can compute amplitudes in order to obtain these extra terms. These amplitudes are related to interactions in a string theory. We have beta functions computations. We can perform beta functions. We can try to preserve Weyl invariance, local Weyl invariance at the level of the effective theory. And this is another way to obtain alpha prime corrections. Both methods are very difficult to perform if we are in arbitrary backgrounds when the metric tensor is not constant. And we have a third method over here that it's related to symmetry arguments. For example, some symmetries could fix the coefficient of the Lagrangian. This is, for example, what double field theory does. Here we are going to talk about double field theory today. We have symmetry arguments. But before going to the double field theory part, before focus on the symmetry arguments, I would like to show you a a kind of for method to obtain the alpha prime corrections in the heterotic case, and this method is due to a relation found by Berkshire and the rule. So let me review some things about this version of the rule identification. I am going to review some aspect of the previous lecture in order you to recall the kind of terms. And in order to perform this version of the rule identification, we will start with this. We have to think in this identification as an alternative method. This is an alternative method to obtain alpha prime corrections. But this method only works for the gravitational four derivative terms. So for us, it's okay. Then we are going to introduce double field theory, heterotic double field theory. This will have more ingredients than Gianluca's formulation, because heterotic double field theory is a gauge double field theory. So we are going to introduce that kind of double field theories. And finally, we are going to review, or we are going to introduce the generalized Green-Schwarz mechanism, that it's a Green-Schwarz mechanism, but at the DFT level. So if you have questions, of course, try to ask. In the previous lecture, we analyzed this Lagrangian over here. This Lagrangian contains alpha prime corrections. We have higher derivative terms, and we have two parameters. When we choose the parameters, when we choose parameters in a particular way, we obtain alpha prime corrections. This is a higher derivative Lagrangian. The alpha prime corrections appear when A is equal to -1 and B is equal to -1. That's the bosonic case. And for example, we don't have these kind of contributions. We don't have Chern-Simons terms in the case of the bosonic string. Then we have alpha prime corrections when A is equal to -1 and B is equal to 0. That is the heterotic, these are the gravitational heterotic corrections. And finally, type 2 doesn't have this kind of terms, so it's the trivial election, both parameters 0. And let's recall that this kind of terms contain Riemann square term. We have Riemann times h squared. We have h to the 4 terms. All these terms contain 4 derivatives. This kind of writing, this two-parameter family, was first introduced by Marquez and Núñez. Is reference 14 in my notes, and it's a very good way to introduce higher derivative terms, because double field theory will reproduce all these combinations, all this kind of higher derivative terms, not just the bosonic case or the heterotic case. From double field theory, we are going to reproduce all these families. Of course, different A's and B's gives theories that are not string theories. If A is not equal to -1 and B equal to 0 or -1, we are in a different theory, not in a string theory. We have higher derivative corrections, and that higher derivative corrections are compatible with double field theory, are compatible with T-duality. I will be more clear in some minutes. So these empty actions requires a first order Lorentz transformation. We analyzed this in the previous lecture. This is a Green-Schwarz mechanism. This mechanism is not present in the bosonic case. The bosonic case is A equal to B, so it's not present in the bosonic case when we write things in the MT formulation, in the Metzave-Zeitlin formulation. We don't have this, we don't need to deform the transformations in that case for the bosonic string. And the reason is that the problem in the previous Lagrangian is that this is the only non-covariant term. Let me go up just for a minute. All this term here, these terms, I'm going to change my color. This term is fully covariant. We can write this object in terms of the spin connection, but it's fully covariant because it's a tensor. This is a tensor, so it's covariant. And the only non-covariant term over here is this. These are covariants. all these terms are covariant, and this is the non-covariant one. This combination here is non-covariant. So for example, in the bosonic string, we don't have this term, so we don't need to deform the transformations. We don't need a Green-Schwarz mechanism in the bosonic case. In this framework, in the medsafe settling framework, and if we are in a case where A is not equal to B, we need to deform our transformations. We need a Green-Schwarz mechanism. So let's continue. When we deform the transformations, the action is Lorentz invariant, the complete action. The action is Lorentz invariant. Why? Because the first order transformations act in the zero order part. The first order transformations transform the H term, because it's the only term which contains the B field. This term over here now transforms under Lorentz transformations, and the first order action, this over here, transform under the zero order transformation, and both contribution exactly cancel. Of course, you can ask what happened with this kind of contribution. For example, we have the Green-Schwarz mechanism acting on this term, acting on this one. This transform under this transformation. We can transform in this way, but this is an alpha prime square contribution, because we have two derivatives over here. We swap a V field by two derivatives, and now we have a 6 derivative Lagrangian. So this combination just affects higher order contributions. We can neglect that kind of contributions. So we are not transforming with first order transformations, the first order Lagrangian. This is a second order contribution. So we can discard this contribution. And the action is Lorentz invariant at the alpha prime order, in this order. So if we consider covariant and non-covariant field redefinitions, we need both field redefinitions. We can change the form of the medsafe-settling action and write that action in this way. This is the Birch-of-the-Roux action. This is the Birch-of-the-Roux action. It contains the same information. This action is very related to string theory. It contains the alpha prime corrections for the bosonic string and the heterotic string when A and B takes the values that you already know. This is the same actions in terms of the physical point of view. We are only performing covariant field redefinitions and non-covariant field redefinitions. And in this case, we have only Riemann square terms. For all these theories, we have Riemann square term. This is our Riemann square. But now the Riemann tensor is constructed with a spin connection that includes a torsion term. This is the torsion term. This is our new connection. When we use minus, we have -1/2 term over here. And when we use the plus, it's just +1/2h. This is the torsion. This torsion term doesn't affect the way that the spin connection transform. This is still a connection, since this h is covariant under Lorentz transformation. These mixed indices, means that we have this object, and we are rotating indices in this way with two field lines. But these field lines are fully covariant. This transform as vectors. So this object transformed in a covariant way. So it's a good connection. It's a good torsion. And this is just another way to write this action. This is the Birch-of-the-Roux action. So, for example, if we want to prove that this action is Lorentz invariant, we still need a Green-Schwarz mechanism, but it's not the same Green-Schwarz mechanism as the previous one, because we have field redefinitions. So we have a new Green-Schwarz mechanism. This is different. We have an extra term over here. Sorry. We have an extra term in our Green-Schwarz mechanism. Our B field transform in a different way. So both B fields are in some sense are different. Both B fields are connected by non-covariant field redefinitions. We need this extra term over here, this term with H and the connection, in order to reproduce this extra term. The Metsaev-Zeitlin B field, if you want to recall this transformation, for the Metsaev-Zeitlin B field transforms only when with the first term. We have this only the first term. And the other term, in some sense, is including torsion in our connection. This is the transformation for the Metsaev-Zeitlin B field, and this is the field redefinition that we need in order to make this term over here to appear. So we use this kind of field redefinitions when we need to change the transformation rule of a field. It's not always possible, but sometimes we can change our transformation rules using these non-covariant field redefinitions. So, for example, in the heterotic supergravity, when we choose the parameters in this way, we obtain a Riemann square contribution in this way, and we have these Chern-Simons terms over here. The Chern-Simons terms are constructed with the spin connection with torsion, of course, and we have a Green-Schwarz mechanism for the B field. This is a gravitational. This is a gravitational Green-Schwarz mechanism. This is a gravitational Green-Schwarz. Of course, in this case, we are showing the heterotic supergravity with an alpha prime correction over here, and we are considering, if you want, that this is the engaged part. We can consider that this field is turned off. Why is that? Because if we turn on these fields, beside these contributions, we have the Yang-Mills term, the F squared term, plus alpha prime corrections to the gauge sector. We could have, for example, F to the 4 terms over here. We are focused only on the gravitational terms. So this is the heterotic supergravity with an alpha prime correction for us. All the Riemann times H terms or H to the 4 are inside this new Riemann that is constructed with a spin connection with torsion. And the form of the verge of the root action is very interesting, since it has the form of a Yang-Mills action. This is the most important part. These field redefinitions turn the action into a Yang-Mills action, but it's near a Yang-Mills action, because in the previous slides we have here 1/8 Riemann squared term. And here we have an F squared term. The structure is very, very similar. We have a lot of analogies between the alpha prime corrected in the gravitational sector and this zero order. This is the zero order Lagrangian. We go back to the heterotic supergravity without alpha prime corrections, and this action is very similar to the previous one. We have these Chern-Simons terms. These are gravitational Chern-Simons terms. We have a Green-Schwarz mechanism. This is a gauge Green-Schwarz mechanism. This is a gauge Green-Schwarz. We have the Chern-Simons terms. This is very, very similar. So the idea is to perform an identification in order to turn the gauge part, all the gauge degrees of freedom, all the gauge symmetry. We want to turn this gauge symmetry into gravitational degrees of freedom or gravitational symmetries. In doing so, we are going to obtain the alpha prime corrections from an alternative method. This alternative method is the verge of the root identification. So in order to identify fields, we need that these fields transforms in the same way. And we observe over here that the gauge connection transforms very similar to the spin connection with torsion. Let's try to make some analogies. We have, for example, a connection term over here and a connection term over here. We have the derivative of a parameter. One is a gauge parameter, the other is a Lorentz parameter. but it's very similar. The structure is very similar. Then we have this contribution that it's a covariant. It's a covariant gauge transformation. And over here we have a covariant Lorentz transformation. These are very, very similar. And of course, we have the first part that it's related to that both fields transform as one forms with respect to diffeomorphisms. So this is, of course, similar to this. So the idea is to identify both fields. It's a formal identification. I'm going to show you heuristic arguments, very heuristic arguments, but this is a very formal identification. It can be performed with a very mathematical detailing. So the verge of the row identification is this one. This is the verge of the row identification. We are always going to think in this direction from gauge. We are thinking from gauge to gravity. We are thinking in this direction, but of course the map is invertible. You can turn gravity into gauge terms. And we want to convert or to turn this term into this term, and we want to turn this gravitational Chern-Simons term into Lorentz gravitational terms. This is the idea of the verge of the row identification. This identification was used a lot in order to construct higher derivative terms. For example, if you analyze my reference number 9, in the reference number 9 of my lecture notes, you have the original publication of verge of the row. These are 2 papers from 1989. And in these papers, they use this identification in order to construct the alpha prime terms, and they go beyond. They try to reach alpha prime cubic terms. So you can read the original paper. It's very interesting. It's a very interesting paper. They also included supersymmetry and this identification. They try to preserve this identification to higher orders, but this identification cannot be preserved to higher orders, but supersymmetry fixes the coefficients anyway. So they mix both methods, the identification and supersymmetry, in order to construct the higher derivative terms. So let's go on. Here we have gauge generators. The gauge generators, we are going to use these gauge generators in order to turn the gauge degrees of freedom into the gravitational one. We have these 3 equalities over here. The products with gauge generators are going, gives us some delta functions. And these strange terms over here is just to reproduce the election of the heterotic case. We can reproduce a generic parameter. We need to change a little bit this last relation, but we can reproduce a different parameter of the Riemann square term if we are, for example, in a kind of scaling of the heterotic case. We can reproduce always one parameter. Also, we can reproduce the B parameter if we identify with a spin connection with the plus index. And this is possible. I am going to show you just this case that it's the heterotic case. So every vector, every gauge vector will turn into a gravitational vector or a Lorentz vector, and every gauge parameter is turned into a Lorentz parameter. So if we perform this identification and we try to understand what kind of transformation has this new field, we have a new field over here that it's a gravitational field, and this new field transforms in this way. So if we identify this new field with the spin connection with torsion and this new parameter with the Lorentz parameter, we have exactly the transformation of a spin connection with torsion. This is a very good news to us, because we are going to reproduce the alpha prime corrections just with this identification between the gauge field and the spin connection with torsion. These are our identifications. These are our formal identifications. We only need these 2 identifications over here, plus the gauge generators relations. With those equations is enough to obtain the alpha prime corrections in the heterotic case, the gravitational ones. So for example, the curvature, this curvature over here, this field strength, turns into this, that it's exactly a Riemann tensor. You have an overall factor, the relation is this one. This is part of the exercises. I think this is exercise 13 of the list 1 of the list of the first lecture. You have to reproduce these computations. Of course, I am helping you over here. The idea always is the same. We need to first to turn one gauge connection into a gravitational one, like this. We are changing the fact. I don't know if we are changing or not. I think that this is not changing because we have two connections. Then we try to multiply the structure constant with the generators and obtain these other terms, and then we just turn all our connections, our gauge connections, into gravity, into spin connections with torsion. So this works for the curvature, and of course it's going to work for all the terms. For example, the Green-Schwarz transformation. If we start from here we have this is the gauge Green-Schwarz. This is the gauge Green-Schwarz, and finally we obtain the gravitational Green-Schwarz in 4 lines. The gravitational Green-Schwarz. This is the idea of the Birch-of-the-Roux identification, to turn the gauge symmetry into Lorentz symmetry, into a higher order Lorentz symmetry. For example, for the Chern-Simons terms, here on Slack, I upload these slides, and I had a typo over here, and thanks to Sergio Aguilar that some minutes ago made me notice of this typo. This is okay now. Here we are turning the Chern-Simons term, the gauge Chern-Simons term, into the gravitational one. Everything works very well. So the Birch-of-the-Roux identification can be used to construct the 4 derivative gravitational terms in the heterotic supergravity. And the main idea of this identification is to turn the 0th order non-abelian gauge sector into a 1st order gravitational sector. So the main idea of this identification is to start with this, with the gauge Sugra, and this 0 order gauge Sugra turns into just a Sugra plus alpha prime corrections. These alpha prime corrections, of course, are 4 derivative terms, gravitational 4 derivative terms. So our goal is to mimic this identification at the DFT level. We want to start with a gauge DFT. We want to start with a gauge double field theory to perform a kind of generalized identification, and then obtain a DFT plus alpha prime corrections, or plus higher derivative terms, if you want. If double field theory is not still a string theory, we can think about higher derivative terms over here, and these higher derivative terms then reproduce after applying the strong constraint, after parametrizing our fields, or upon parametrization, we find the supergravity Sugra plus alpha prime corrections. This is the map. This is our idea. We want to generalize this identification, but before performing all these ideas, I am going to introduce gauge double field theory, because gauge double field theory contains more ingredients than Gianluca's version. Gianluca works with the ungauged double field theory, and we are going to complete the extra ingredients that we need in order to perform the identification. We need gauge fields and gauge symmetries in double field theory in order to perform a kind of generalized Birch-of-the-Roux identification. Our idea is to go to the generalized Birch-of-the-Roux identification. Of course, the idea is not thinking in the 4 derivative terms only. We want a systematic procedure to obtain a tower of alpha prime corrections, and then we need comparisons with other methods like scattering amplitudes or beta functions computations, in order to show that our deformed double field theory, or our double field theory plus higher derivative terms is consistent or is correct. So I am going to start with some motivations, just a few minutes. Everything here was already said by Gianluca. I'm just trying to match with him. But let me know if we have questions, because perhaps someone has a question. Everything is fine. Okay, let's try with some motivation about T-duality. This motivation is before double field theory. Why we want a double field theory, or why double field theory is interesting. So if we focus on the low energy effective action for the bosonic string, we are, in this case, the low energy effective action for bosonic string, and we compactify on a d-dimensional torus, and we have an internal space and an external space. Our external space is n-dimensional, and our internal space is d-dimensional. The resulting theory is invariant under this group. This is the T-duality group, ODD seed. In its simplest form, for example, if we compactify on a circle, the simplest form, in its simplest form, this symmetry indicates that string theory compactified on a circle of radius r, this one over here, and strings with momentum p equal n is an integer. This is completely equivalent to a theory compactified on a different circle. This equality over here, if we use alpha prime, should be alpha prime over r. And we always are using alpha prime equal to 1. And that's why we count derivatives in order to understand the order of each term. But if you change the geometry in this way and you change winding momentum, or took winding momentum omega equal to n, these both scenarios or these both frameworks are completely equivalent. This is the T-duality. This is a symmetry, and the symmetry group behind this duality is ODD seed. So on the left, we have a string with momentum p, and on the right, we have a string wrapping over the compactified dimension. This is the simplest case, just the circle, but it's good to understand the duality. So before compactification, we are dealing with this Lagrangian, and this Lagrangian is invariant under infinitesimal diffeomorphisms and abelian gauge transformations. But this Lagrangian over here is not invariant under ODD seed. This is the T-duality group, recall, this is T-duality. But this Lagrangian is not invariant under this group because we are before compactification. We are always working before compactification. So this small d over here means nothing to us. We work with capital D. We work with all our dimensions, arbitrary. We are not compactifying anything. So the idea is that diffeomorphisms, the idea here is that diffeomorphisms and abelian gauge transformations can't fix these coefficients, can't fix this 4 and this 1 over 12. We can change these numbers, and the Lagrangian is still invariant under abelian gauge transformations, and the action is still invariant under infinitesimal diffeomorphisms. So these symmetries are not good to fix the coefficients in the Lagrangian. So the idea is to use a symmetry very, very close to T-duality. We are going to try to accomplish this symmetry. This is the symmetry group of double field theory, is ODD-R. Capital D is because we are not working in a compactified space, so we are working, we are analyzing just the full story. We have all our dimensions very arbitrary. So we have this ODD-R with capital D, and R is related to the case that we don't have a compactification, so we don't need to use the discrete group. So if we accomplish ODD-R as a symmetry group and we construct this double field theory, the coefficients of the supergravity Lagrangian are fixed. these coefficients are fixed by this duality group. This is not exactly T-duality, it's very close to T-duality, but this symmetry fixes the coefficients of the Lagrangian. In some sense, double field theory is not a string theory, but contains information about strings. The geometry of double field theory, that it's not a Riemannian geometry, that geometry contains a lot of information about the string theory. And we can fix coefficients in the Lagrangian without working explicitly with a string theory. That's the power of double field theory, that we can fix coefficients, we can find a supergravity upon parametrization and using the strong constraint. So this part is very important. This is just philosophy. It's the philosophy of double field theory. This double field theory can be understood from at least two philosophies, I think, in double field theory in these two ways. On the one hand, we can think on double field theory as a rewriting of Sugra, which is the direction, in this case, is this direction. We are thinking that our fields, we have our supergravity, our fields are in multiplets. I took, for example, G and B from the supergravity, and I put this on a generalized metric, for example, and I took this determinant over here and this dilaton over here, and put this on a generalized dilaton. This is a way of thinking double field theory. That's a rewriting of supergravity, of Sugra. But there's another way that it's important to us. We are always thinking with the second philosophy. We are not thinking as a rewriting. We are thinking that we are constructing an ODDR invariant theory. We start with this. We start here. This is our starting point. We construct an ODDR invariant theory, and then this theory reduces to supergravity. But our starting point is double field theory. We are not starting from supergravity and performing a rewriting. We are just constructing a T-duality invariant theory, or if you want, an ODDR invariant theory. And that theory, upon parametrization and upon strong constraint, reduces to supergravity, but not exactly to a string theory. When we include higher derivative terms, we will reproduce all these AB parameters or family parameters. We have a lot of higher derivative corrections that came from double field theory, and some elections of that parameters reproduce alpha prime corrections. So that is the philosophy. That is the idea of double field theory for us.
Eric, sorry, a naive question on that slide. So you say T-duality or DFT can fix those coefficients 4 and -1/12. But one can always rescale dilaton, the B field, and those coefficients would change. So in what sense do you claim you're fixing the coefficients by T-duality?
Okay, if you perform field redefinitions at the two derivative level, you can always perform that field redefinitions from the double field theory point of view and obtain that action. You can always obtain a supergravity from double field theory, a string,
yeah,
a low
it's
energy.
just a rewriting of your fields, and that's why I don't understand in what sense you're fixing those coefficients, because you can always redefine. Maybe in the case of the dilaton, it's more subtle because it appears also in the exponential. But you can scale the B field with whatever constant you want, and you will change that coefficient.
And this is right, but I mean that the diffeomorphisms and abelian gauge transformations can't fix this coefficient. And from a T-duality point of view, you can choose some coefficients here, and you are always finding that supergravity coming from a double field theory approach.
You're sort of fixing the coefficients because you're deciding what are the T-duality rules that you want to implement, and then that is fixing your normalization, and then that forces these coefficients to be, for example, 4 and -1/12.
Yes, exactly.
But okay.
In some sense, T-duality is symmetry. That here is, if you want, hidden. We don't see T-duality in this level because we don't have compactification over here. But from a double field theory point of view, T-duality is a symmetry that it's present, and this symmetry mixes coefficients, for example, in the generalized rich scalar. So if you want to be compatible with T-duality, your field redefinitions, the field redefinition that you are thinking, must respect that rules. So if you change
that constant rescaling will affect, say, the Busher rules, for example.
Exactly that. You can change your fields if you want, but you are going to obtain that fields from T-duality or from this ODDR group that perhaps some people don't speak about T-duality because it's a bit different, the group, but we can use this group in order to fix that coefficients. Okay, let's move on, but this is the idea. We want a double field theory. We want to deform the double field theory. We want a higher derivative double field theory, and that higher derivative double field theory will fit the coefficients of a supergravity plus higher derivative terms, and some electrons of that higher derivative terms will give alpha prime corrections. And these two philosophies are important because if we always think about rewriting supergravity, we always need the alpha prime corrections, and then we try to reproduce a double field theory. But the idea is not to reproduce the result that we already have. The idea is to construct a systematic procedure to obtain a tower of alpha prime corrections. And if we have luck, this tower, this construction of an ODDR invariant theory with a lot of corrections will reproduce alpha prime corrections. This is the idea. So let's move on. The low energy effective action of the bosonic string can be recovered from an ODDR invariant theory. And I think this was an exercise in the Gianluca's lectures. You have to reproduce the supergravity Lagrangian. And if you and I think I have the same exercise, I think, in my lecture too. So it's you are forced to do something like that. And our goal now is to find a consistent higher derivative deformation, second philosophy, and we start studying the heterotic case. We will study this case, the heterotic case. So let's, we should start with an introduction to heterotic double field theory, but I think that we can stop here 5 minutes and then we continue with this topic.
Okay, thank you. So see you in 5 minutes.
Yes. Thank you, Cyril. Okay, let's continue. Let's start with heterotic double field theory. This is gauge double field theory. We need a gauge double field theory because heterotic string contains an extra massless field, this A field, this gauge field. So we need gauge symmetries at the level of the double field theory, or a structure constant, for example. We need gauge ingredients in our double field theory. So this construction can be performed in 4 steps. We are going to start with the double geometry, then with the symmetries, the fundamental fields, and finally the action principle. This story is very, very similar to Gianluca's story, but we are going to add some ingredients related to the gauge part. So the double geometry. The duality group here is not ODD, is ODD plus n. We need this n is the dimension of the gauge group. It's n over here is the dimension of the gauge group. Sorry, this is an H of the gauge group. For example, for the heterotic string, this gauge group is E8 times E8 or SO32 or spin 32 over C2. The dimension in that case is, well, it's not relevant for us. We can think in a gauge, in an arbitrary gauge group, but we need to consider an extended double space. Our dimension of the double space is larger than Gianluca's because we need a space or room for the gauge symmetry. So our coordinates now contain an extra coordinate over here that it's a kind of gauge coordinate, but do not worry about that coordinate. We are going to impose a kind of constraint to finally obtain only dependence on the x mu coordinate, not in the tilde one and not in the gauge one. And we are using these calligraphic indices because now we have gauge. So we use these calligraphic indices. And on each point of the extended double space, we consider an extended double tangent space. So we are able to define flat vectors. These are our flat vectors for us. We are going to define a generalization of the field. We will have a frame field. And these are our flat indices. Of course, the flat indices runs exactly in the same cases of the curved one. This is exactly the same. And this notation is different from Gianluca. I have, on the Slack channel, I have a dictionary between my conventions and Gianluca's. And Gianluca's was using something like this, a dot over here for this index. He used a dot for the flat indices. And we are using the A, B, C, D letters. So we have an ODD plus N invariant metric. Oh, sorry, this group, ODD plus N, this is the ODD plus N R group. This is our group. And if we turn off the gauge symmetries, we go to an ODD R group. This is our T-duality, if you want, the T-duality group over here. We have an invariant metric. This invariant metric, it's very similar to Gianluca's. Let's observe that we have this block over here. It's the same as Gianluca's, but we have an extra block over here because we need a Cartan-Killing metric. This is with this metric, for example, exactly with the inverse of this metric, we contract indices in the heterotic gauge part, for example. In this term, in the Young-Mills term, these contractions over here, these contractions are performed with a Cartan-Killing metric. So we need this metric because we know that this metric is present in the heterotic supergravity. So this is our invariant metric. Let's observe that all these objects over here are constants. So all our symmetries, all our constraints, all our equation must be consistent with this invariant metric group. This is constant, so the derivative of this eta mn is 0. The transformation under all the symmetries is 0. We need compatibility with this invariant group metric. So, and here mu and nu and I are the supergravity indices. All our DFT objects, all our DFT vectors and parameters, in some sense, contain the supergravity objects. This is kind of philosophy one, that the kind of rewriting of the supergravity. And of course, the flat indices contain the flat indices or the supergravity perspective and a flat index for the gauge. This is the flat version of the Cartan-Killing metric. Again, all these objects over here, all these objects are constant. All these objects are constant, all these matrices are constant. And we have, at the DFT level, we have 3 invariant metrics. At the DFT level, I'm going to change my color. At the DFT level, we have 3 invariant metrics. We have these metrics, these 2 metrics that are invariant under the Lorentz symmetry or the double Lorentz symmetry. And let me go up for a minute. And we have this invariant metric that it's invariant under ODD, under the ODD plus N group. So we have 3 invariant and constant metrics. We have this eta with curved indices, and we have this other eta with flat indices, and this H metric over here with flat indices. This is not the generalized metric. This is just an invariant metric. These 2 metrics are invariant under the double Lorentz group. In double field theory, we have a Lorentz group, a double Lorentz group, and these metrics are invariant under that group. We are going to perform a gauge fixing over here because from double field theory, we obtain these 2 Minkowski metrics, and we are going to claim that both Minkowski metrics are the original one from supergravity. Or if you want, all the small indices with A underline and A overline, these small indices are Lorentz indices for the supergravity perspective. There is a question. I heard a sound. If someone has a question, please go ahead. So, of course, these Cartan killing metrics, sorry, are related. We have a kind of a kind of field line, a gauge field line, if you want. But all these objects over here, all these objects are constant. The derivative of any of these matrices is zero. These objects are constant. So sometimes, instead of using this invariant metric, instead of using these ones, sometimes we use projectors. These projectors, of course, are constant. Sometimes we will use these projectors. These projectors are very useful for constructing, for example, the action principle. These are projectors in this way that the product of two p's gives a p, the product of two bar p gives a bar p, and the product of two p gives a p. This is the relation. We have the sum of the projector gives one invariant metric, and if we do this, these indices are calligraphic. We can obtain the other invariant metric. These are calligraphics. And of course, the product between two p and p bar, or p bar and p, it's zero. So these are good projectors. These projectors are completely constant, but we are going to use them in order to construct an action. So we have symmetries. Let's discuss about symmetries. These are generalized symmetries. These are symmetries from the double point of view. We have generalized diffeomorphisms, but let's observe that we have an extra term over here. We have structure constants. These are, if you want, a generalized notion of structure constant. We are deforming our generalized Lie derivative, or if you want, this is the generalized Lie derivative for gauge double field theory. Gauge double field theory contains an extra term in its generalized Lie derivative. Of course, this derivative acting on the invariant metric is zero, and these structure constants satisfy these relations, are completely antisymmetric, and this is a kind of Jacobi identity for the structure constant. We have an extra term over here, and this extra term over here, this extra term on the generalized Lie derivative, will change our bracket. We want closure of the transformation, and the bracket now contains an extra term. These terms were computed by Gianluca, and now we have this extra term over here due to the gauge part. Of course, if we turn off for example, the structure constant, we obtain the C bracket. I don't remember if Gianluca give you the name. This is the C bracket. It's the bracket of double field theory. This bracket, this C bracket, this is the C bracket, and this C bracket reduced to the Lie bracket upon parametrization and imposing the section condition. This reduced to the Lie bracket, and the CF bracket reduces to a deformed Lie bracket in the case of the heterotic string theory. This is an exercise. You can include this as an exercise to list two. To reproduce the exercise could be go from CF to a kind of Lie F bra. This could be an exercise if you want. We have an extra term over here. We satisfy closure, but the closure of these transformations, recall that force us to impose some extra conditions like the strong constraint, the weak and the strong constraint. So in this case, when we consider gauge symmetries, we have an extra condition. This is the strong constraint. Sorry, I'm mixing the colors. This is what you need in order to the standard generalized diffeomorphism, the ungaged part closed. or clauses. And when you include gauge symmetry, we need to include this as a kind of constraint. You have this constraint over here. And the way we solve this constraint is demanding that the extra coordinates, all our extra coordinates, in some sense, our fields do not depend on these extra coordinates. Our fields, for example, once we parameterize our fields, for example, a tensor metric will depend only, we have all these coordinates, the gauge part, and our fields will depend only on the standard coordinates. This over here means that our fields do not depend on the gauge coordinates, and of course, this over here means that our fields do not depend on the extra coordinates. And for the structure constant, the only non-vanishing components are these ones. This means that, for example, a combination, a different combination, for example, something like this, is 0. And so on. We have a lot of combinations. Well, this is related to closure, to the closure of the transformation. And we have another symmetry because we are in the gauge double field theory, but we want a heterotic double field theory. So heterotic double field theory is a n equal 1 supersymmetric invariant theory. We will have we should have fermionic fields at this level. We are not writing them, but we need the Philbine formalism, or we need Lorentz transformation, the Lorentz symmetry. We need this transformation because we have fermions in some part of this formulation. So this double Lorentz transformations acts in this way. It is my diffeomorphism parameter is this one, and my Lorentz parameter is this one. This is different from the Gianluca convention, so pay attention with the conventions. This is a Lorentz transformation. Of course, this parameter is antisymmetric because we need to satisfy this condition over here, similar to the supergravity case. But we have another condition that is this one, and this means that the mixed component of this parameter are 0. We have only the same projections on these parameters. Recall that these bar indices, the convention for the bar indices, if you see underline indices, this mean, I'm going to change color. If you see underline indices like this means contractions with a P projector. And if you see overline indices like this means contractions with a P bar projectors. This is what bars means for us. Instead of using the eta metric, we use the P or P bar as a metric. This is our convention. So let me erase this. Okay. And when we parameterize our symmetries from the gauge double field theory point of view, these parameters, in some sense, is saying us that the generalized diffeomorphisms, or inside generalized diffeomorphisms, we have abelian gauge transformations, non-abelian gauge transformations, and diffeomorphisms. This means this. Well, I think this is clear. And in this case, this is exactly the same. Here we have double Lorentz transformation. These are double Lorentz parameter, but they reproduce just ordinary Lorentz symmetry. This is the idea of gauge double field theory. It's very similar to the ordinary double field theory, but we have gauge degrees of freedom, and for example, the gauge symmetry, this gauge symmetry over here, is inside the diffeomorphisms is inside generalized diffeomorphisms. That's the idea. So in this point, we can construct a covariant derivative. We can construct a flat covariant derivative. Of course, we can construct the other covariant derivative with respect to diffeomorphisms, but we are always working with flat indices. So this is enough for us. It's enough to construct this covariant derivative. The covariant derivative contains a connection. This is a generalized spin connection. It's very similar to the supergravity case. The transformation is exactly the same. if you see this transformation, the structure of the transformation is similar to the supergravity case. And we are going to use this notation. I think in my lecture notes, I use this notation instead of a nabla. In double field theory, we use a capital D for the derivative. This capital D with an index. We use D for the dimension, but when you see D with an index, this means covariant derivative. This means that the DFT derivative acting on a flat vector is not covariant, but if you use this, if we use this derivative, then it's a covariant. This would be covariant. That's the idea of the covariant derivative. So the fundamental fields. Here we have bosonic fields, because recall that we have fermions. In the heterotic case, we have bosons and fermions. So we are focused on the bosonic part of the heterotic formulation. So our fundamental fields are a generalized frame. This is the generalized version of the field line. Instead of talking about the field line, we talk about the frame. It's the generalized frame and the generalized dilaton. So this is important. This is very, very important, because the fundamental fields are exactly the same as DFT. In DFT, we have a generalized metric and a generalized dilaton. Here we have a generalized frame and a generalized dilaton, but the same means that we do not have a gauge field. We do not have a generalization of the A field, the extra massless field for the heterotic. We do not have that kind of field in gauge double field theory. We have the same fields. We have, if you want, the generalized metric that can be constructed from the generalized field line of the generalized frame, and we have a generalized dilaton. But that's all. We have the same fields as double field theory. So you know that the generalized frame is a vector, and the generalized diffeomorphism and double transformation, and the generalized dilaton is a double Lorentz invariant. The generalized dilaton is a double Lorentz invariant. This is new for us. And this combination, e to the minus 2d, is a scalar with this weight, with weight 1. This means that the transformation of the dilaton under diffeomorphisms is non-covariant. This is a non-covariant transformation. We have a covariant part, we have a transport term over here, but here we have a non-covariant term. This is a non-covariant term. And this is what happened in a standard double field theory. This is the same as Jean-Lucas have told to you. The dilaton does not transform as a scalar, but this combination transforms as a density. So it's a good measure. So the generalized frame is parameterized in this way. Inside the generalized frame, inside this field, this is a typo over here. This should be calligraphic. Inside this field, we have the ordinary field line. We have this combination of B field and A field, and we have, if you want, the gauge field that is inside the C field. What I want to say here is that our generalized frame, this object, depends in some way, when we parameterize, depends on the ordinary field line, on the B field, and depends on the extra A field. And this parameterization is different to Jean-Lucas, even when you impose the gauge field equal to 0. This parameterization is different. Jean-Lucas uses the triangle parameterization, and I am using this parameterization since this parameterization is compatible with supersymmetry. Or it's more convenient when you introduce supersymmetry. That's all. And of course, the parameterization of the generalized dilaton is exactly the same. This is our parameterization. So in some sense, the dilaton depends on the determinant of the metric and depends on the dilaton, on the standard dilaton. Of course, we can write this relation as the determinant of the field line times this object. If we want to write everything in terms of the field line. You can write everything in terms of the field line. This is our parameterization. And if you observe, we have a pair of field lines, but this is a kind of gauge fixing from double field theory. We recover two field lines. This is very related to the projectors scenario. Double field theory is like a chiral theory. We have two copies of supergravity if we want. We have two field lines, but this is a gauge fixing. Both field lines reproduce the same gravity, the same metric tensor. So we just need to consider a gauge fixing when we work in this formalism, in this field line formalism. We obtain two field lines from double field theory, and we claim that both are the same field line. So the gauge fixing is related, of course, with fixing some parameters, and these extra parameters, this extra Lorentz parameter, cannot be arbitrary. These extra parameters over here, this combination with extra indices, must be this combination in order to preserve the consistency of the theory. For example, we want that this object do not transform, and we have another condition that is that, let me recall, we have two conditions. We have this condition, let me see the parameterization. We want that, let me change color. We want that this component do not transform, and we want that this component do not transform. Sorry, I highlight again. We have gauge fixing over there. When we transform that combination, the transformation of this must be 0, and the transformation of this must be 0. These are gauge fixing. These are gauge fixing. These fix parameters in double field theory. I think that is an exercise too. So that we have this condition and we have the other condition. We have two conditions, and we obtain these extra parameters, if you want, this relation between the gauge parameters and the Lorentz parameters in double field theory. This is a gauge fixing. So we have this object over here are very, very interesting to us. These are the generalized fluxes. These generalized fluxes are very interesting to us because we are going to write our action, our rich scalar, in terms of this object. I have this combination over here, and this combination over here that determines the antisymmetric part of the spin connection. The antisymmetric part of the spin connection is fully determined in double field theory. We have extra combinations that are not fully determined, but the antisymmetric part is determined. And here the notation is that an E with one index is this square root of 2 is related to our parameterization. We use parameterization that is more convenient for supersymmetry. That's why we have a square root of 2 in some cases, just like this. But this object will be very, very important with our rich scalar. The generalized rich scalar will be constructed in terms of these fluxes. Will be constructed in terms of these fluxes. We will use the flux formulation of double field theory. Any questions over here? I know everybody is hungry. Just a few minutes more, and that's all. I think that the idea is very similar to Gianluca's double field theory, but we have extra term, and we have these fluxes over here. At this point, I forgot a term. I am realizing that I forgot the term over here. Let me correct this. I have an extra term over here because I am in the gauge formulation. Let me check my notes to see the conventions. Just 1 minute. I have an extra term over here. This contains a structure constant over here. Let me see. I forgot this. Sorry. It's in the gauge part. This is equation 2.30. This is equation in my lecture note. This is 2.36. And here I forgot this term, the gauge part. I write the ungaged part. We have here this combination with field lines MA or frames MB and PC. This is important. I just copy and paste the engaged part, sorry. We have this other term, our fluxes contain this term and this extra term, sorry, this extra term that contains the structure constant over here. This is our definition of the flux with a plus over here. This is our definition. Okay, and we can match all these objects. We can with all these objects we can identify the generalized spin connection if we want, the spin connection of double field theory. Okay, so let's move. If you observe the generalized fluxes are we can parameterize the generalized fluxes. This is also an exercise, and some components are very important to us, like this one and this one, because this component of the generalized fluxes are very related to the spin connection with torsion. Here we see some relations between double field theory or gauge double field theory and the Virchow-de-Roux approach. The connection appears with torsion from double field theory. So the Virchow-de-Roux approach will be the indicate approach to connect with double field theory. So, and these terms over here, for example, with a structure constant is related to the term that I forgot in the previous slides. We can reproduce these terms if the structure constant are in the fluxes. That was a mistake. Then I correct the slide, and I recall that in my notes is equation 2.36. I think I write that. Yes. Okay. And from the gauge double field theory, we can reproduce this Chern-Simons three form with the gauge Chern-Simons terms. So this gauge double field theory formulation is very convenient to rewrite the heterotic supergravity, the low energy limit of the heterotic string. Okay. Finally, the rich scalar is written in terms of the fluxes. This is our rich scalar in terms of the fluxes. Recall that the projected indices means that our metrics are the projectors. We are using the projector as metrics over here. And the double field theory on the gauge double field theory action is the same as the ordinary case. This is the same action of double field theory in terms of the fluxes, but the fluxes contain an extra term. This is this term that I forgot in the previous slide. This extra term gives us the Yang-Mills part of the supergravity, of the heterotic supergravity. So this this one index fluxes is defined in this way. And we can reproduce heterotic supergravity upon parametrization, and of course using the strong constraint, and this strong constraint is the ordinary one, plus this extra condition that we have in order to the generalized diffeomorphisms clause in this gauge double field theory. This is what I call strong constraint here. Okay. Here you have the exercises. The exercise to prove this closure condition from the engaged part was already done by Gianluca.
Eric, you have a question. So
yes.
I'll read the question. Is there a geometric reason for the connection between fluxes and the rich scalar?
A geometric reason for the connection or the relation between the fluxes and the rich scalar. Well, yes, it's a geometric. There are a geometric reason because these fluxes transform as connections in double field theory. So this is a kind of relation between. If you focus on the standard Riemann tensor and you write that in the Filbert formalism, you can write this rich scalar in terms of the spin connection, and this is exactly the same. It's the same reasoning, but in double field theory you can construct a rich scalar and a Ricci tensor, but in double field theory we do not have a Riemann tensor. We cannot define a Riemann tensor. So there are a lot of geometric and geometric relations between standard geometry and the double field theory geometry, but it is not exactly the same. I don't know if interesting. Thank you. Okay. Is there other question, perhaps? Recall that in double field theory, in DFT, we can construct a Ricci scalar and a Ricci tensor. This can be constructed, but we cannot construct a Riemann object. And if we can't construct a Riemann tensor in double field theory, we can think that we cannot obtain alpha prime corrections, but because we don't have a Riemann tensor at the DFT level. But we are going to construct alpha prime corrections, and it's not important that we do not have a Riemann tensor in double field theory. And the geometry of double field theory is very, very different from the ordinary one. We have two metrics. We have the invariant metric, the group invariant metric, and the generalized metric. We have an invariant metric and a dynamical metric, but we cannot construct, for example, geodesic equations. This geometry is very, very different from the ordinary geometry, but it's a powerful geometry to fit coefficients in the Lagrangian. That's why we use this kind of frameworks in order to construct supergravities. The supergravities are very related to string theory. Double field theory, in some sense, includes a lot of aspects of string theory. Perhaps it's a bigger family, double field theory, with respect to string theory. Okay, so here we have the exercises. This yellow mark means that Gianluca have already done this part, but you can, of course, do the gauge part. And you have a lot of exercises, so we can enjoy this part. And here we have just to summarize in order to clarify some points. In terms of our four-step construction, we start with the double geometry. And in this double geometry, we have three invariant metrics. Our three invariant metrics are the group invariant metric and the double Lorentz invariant metric. We have these invariant metrics. Of course, with these metrics, we can construct projectors. These are our three invariant metrics. These are the main ideas in order you to focus on. Then we have generalized symmetries. In gauge double field theory, we have diffeomorphisms. These diffeomorphisms give us the abelian, this is the zeta parameter, the non-abelian transformations, and the ordinary diffeomorphisms. And we have double Lorentz transformations. These are double Lorentz. That reduces to the ordinary Lorentz symmetry, but we have here gauge fixing, some gauge fixings. In this case, these are the symmetries. We have diffeomorphisms, generalized diffeomorphisms, and double Lorentz transformation. The double Lorentz transformation closes it's easy to prove that the closure is satisfied. You can see a lot of closure conditions in my reference number. Let me check. Give me 1 sec. The closure conditions are very well computed in reference number. I cannot find the reference. Well, then I told you the reference. It's a paper with a lot of closure. Can be checked in a paper with Rodriguez, Núñez, and myself. You can check the closure between Lorentz transformations, mixed transformation between diffeomorphisms and Lorentz, or you have the closure of the higher derivative deformations. We have a lot of closure conditions in that paper. I can find the number of the reference in my notes, but it's there. So about the fundamental fields, we have exactly the same as double field theory. We do not have a gauge field over here, same as DFT. Our fundamental fields are a generalized notion of field, this a frame, a generalized frame, and a dilaton. And it's important to highlight that here we do not have something like this, something like a gauge field with this kind of indices, for example, plus a gauge index, plus a generalization of a gauge index. We do not have this kind of terms. We do not have gauge fields at the level of the gauge double field theory. This gauge field is inside the generalized frame. So this is important to us for the next lecture. And finally, the action is in terms of the fluxes. So in these last 4 minutes, I am going to start talking about the generalized Green-Schwarz mechanism, and in the next lecture, I finish this part. So in the first lecture, we show that this is, and also in this lecture, we show that the B field transforms in this way in the version of the Roux approach. This is the gravitational Green-Schwarz mechanism. And our goal now is to deform the transformation of the generalized frame, this transformation over here. The transformation of the generalized frame is this, the transformation of this object. We are going to turn off the gauge part. Now these indices are the ordinary one. We are working in ODD, just for simplicity. This transformation is the Lie derivative of this object, the generalized Lie derivative, plus a Lorentz transformation. This is the transformation. And we want to construct a higher derivative double field theory formulation. So we want here a generalized Green-Schwarz mechanism. We want here a generalized Green-Schwarz mechanism. This is our idea. This is what we want. We want to deform double field theory. We want to deform the transformations, and of course to deform the action, the two derivative action. All the terms in the action of double field theory contains two derivatives. We want 4 derivative terms. So we want a generalized Green-Schwarz mechanism. And the idea is to consider a generalized Green-Schwarz mechanism at the DFT level, as I am saying. This factor over here, these 2 over here, this is what we want, a generalized Green-Schwarz mechanism. The natural proposal for this kind of mechanism is to include a generalized flux over here, because this flux is related to the spin connection with torsion, and some derivatives of the parameter. This is very natural. The over 2 parameter is just that we want that this A to be the same A as the version of the Roux approach or the Metzeib setting approach. We want the heterotic case when A is equal to -1. So that is the extra 2 over there to respect conventions. This is a natural proposal. And since we have different projections over here, since we have different projectors, we have different Green-Schwarz mechanism if you want. We have a T1 and a T2. We have 2 Green-Schwarz mechanisms, but both mechanisms are related. If we know T1, we know T2. It's very easy. That's because we have an invariant group metric. So both mechanisms are related. In fact, we can construct the Green-Schwarz mechanism in this way. This is the generalized Green-Schwarz mechanism. This is a deformation. Let's observe that we are deforming only the Lorentz symmetry. We are deforming. Let me write that. We are deforming only Lorentz symmetry. Why Lorentz symmetry? Well, because we want the generalized Green-Schwarz mechanism. But is it possible to deform the generalized diffeomorphisms, for example, and construct a higher derivative double field theory without touching the Lorentz part? considering the standard Lorentz transformation and the diffeomorphisms, that is possible in a different theory. It's called HSC theory, that it's a different combination of A and B. There exists a theory that is obtained deforming the diffeomorphisms. It's a very interesting theory. You can read about that theory in my lecture notes. And if you are interested in that theory, you can read the papers related to that theory. This theory is interesting because it's a Higher derivative theory which corrections are very similar to alpha prime corrections. We can obtain heterotic alpha prime corrections or bosonic alpha prime corrections analyzing HSC theory, but we not can reproduce all the terms. We can reproduce some terms of the alpha prime corrections from the HSC theory, that it's a theory that diffeomorphisms instead of the Lorentz transformations. It's different that it's different to this, but you can read about that in my lecture notes. I am not going to review that theory, but in the next lecture, I am going to continue analyzing the generalized Green-Schwarz mechanism. And finally, I am going to show you a systematic procedure to obtain this kind of deformations, and this procedure works to all orders, to go beyond the first order, and can reproduce some terms in the heterotic case with, I don't know, 6 derivatives or 8 derivatives. It's not the whole story, but it's a systematic procedure. So thank you very much.
Very well. Thank you, Eric, for this nice lecture. Let's give him a round of applause. All right, so I suggest to move any possible question to Slack. So we will now have our lunch break for 1 hour and a half.